Hello, this is Steinmuli, Assistant Professor, Department of Chemistry in Sacred Heart College. So today we are going to learn about coordination chemistry. So today we are starting an introduction to coordination compound. Before that, a complex. If a complex means it contains a metal ion and a ligand. Metal ion which has no lone pairs of electron, whereas the ligand has a lone pairs of electron in its outermost orbital. So let's see what is coordination. When an orbital of a ligand with lone pairs of electron in it which overlaps with an empty orbital of the metal. So from this you know very well the ligand must have a lone pairs of electron and the metal ion which has the electron deficiency center, and the metal and ligand will form a coordination covalent compound. What does mean by coordination covalent compound? So coordination covalent compound is nothing but dipolar bond. So dipolar bond or dative bond. It means two center metal and ligand, it will form a coordination covalent bond. Coordination covalent bond. So two center, one is metal, another one is ligand. Metal has no electrons, no lone pairs of electrons in its outermost orbital, whereas only ligand has two electrons. So these two electrons are donated to the central metal atom, then it will form a dipolar bond, or we call it as coordination covalent bond. So from this it is very clear that ligand must have a lone pairs of electron in its outermost orbital. And then let's see metal ligand bonding. The bond is formed between a Lewis acid and a Lewis base. Here the Lewis acid is a central metal ion and a Lewis base is a ligand. Look at the example. So the ligand Lewis base having non-bonding electron, that is a lone pairs of electron, so ammonia, and then the metal Lewis acid which has empty orbital Ag plus. So then it will form a coordination covalent bond. Look at the example, and then once we are adding ligand to a metal, there will be change in geometry and then such as color, oxidation and everything. And then coordination compound. So what is the difference between coordination complex and a coordination compound? A central metal atom bonded to a group of molecule or ions, we call it as metal complex. So this metal complex, if it is charged, it is a complex ion. A compound containing a complex or call it as coordination compound. And then let's see the basic. Look at the example. So hexamine chromium 3 chloride ions. So this is the example. From this example you are going to know about coordination sphere, ionization sphere or counter ion and coordination number. First we start with coordination sphere. So coordination sphere means the central metal atom and the ligand attached to it or written in a square bracket is called it as coordination sphere. And then the next one, ionization sphere. So ionization sphere is nothing but the cation or anion outside the coordination sphere. We call it as counter ion or ionization sphere. So example is here the coordination sphere is within the coordination sphere Cr and NH3 6 times, that is hexamine chromium within the coordination sphere, and outer the coordination sphere Cl3 ligand is there, that is called counter ion or ionization sphere. And then next one, coordination number. So you know very well already the coordination number means the number of ligand which are directly attached to the central metal atom or cation, we call it as coordination number. So look at the example. So Cr chromium, that is the central metal atom, and then NH3, it is the Ligon. There are six NH3 Ligon are attached to the central metal atom. So that 6 represent the coordination number, and then Cl3, that is ionization sphere or counter ion, and the overall within the square bracket we call it as coordination sphere. And then ligand. Let's see the outline about ligand. So ligand, it must contain a lone pairs of electron. So ligand, it is a molecule or ion coordinating to the metal, we call it as ligand. So they are usually anions. As I told you already, it is a ligands or Lewis base. And Lewis base, or we call it as nucleophile. So look at the example. So water, ammonia, chloride ion, and then Cn minus ion. So the ligand must have lone pairs of electron, and this lone pairs of electron must donate to the central metal cation. So and then the next important evolution of coordination complex is start with the Turbonus theory. Turbonus theory, it is suggested by Werner in the year 1893. So he derived the theory with the two aspects. One is primary and secondary valency. Primary valency and secondary valency. Primary valency is equal to the metal oxidation number, and secondary valency is the number of atom directly attached to the central metal atom. It is nothing but the coordination number. So primary valency represents the oxidation number of the complex, and then the secondary valency represents the coordination number. So look at the example. Werner first obtained a compound cobalt complex. So COCl3 and 6NH3. So look at the example, the original formulation formulated by Werner, COCl3 6 ammonia. It is in orange color, whereas the same complex but different ammonia. For example, COCl3 5NH3, it is in purple color. COCl3 4 ammonia, it is in green or violet color. So now just think why it is like this. So the exchange of ligand, both primary valency and secondary valency according to Werner, or the ligand NH3 and the chloride ligand. So the modern formulation is hexamine cobalt 3 chloride ion. So that is the modern formulation. So here the modern formulation, the chloride ion Cl3, it is the primary valency, and then the 6 ammonia ligand, it is the secondary valency. So this was the example, and then Werner proposed to putting all the formula and ions within the coordination sphere in a bracket, and those are free ions or outside the bracket or primary valency. Within the square bracket we call it as secondary valency. And this is the example. So the violet color complex, this approach correctly predict there would be 3 forms of COCl3 and then 4 NH3. Then the modern formulation is written as CONH3 4 times Cl2 Cl. So the exchange of chloride ligands within and outside the coordination sphere. So the color is depending upon the chloride ligand. That is what Werner concluded. And then oxidation number, it is very basic. How to find the oxidation number of a complex? Let us consider the example tetramine copper 2 plus complex. So you have to find out the oxidation state of the complex. So you know very well, amine, it is a neutral ligand. So 4 into 0, then it will become 0. Therefore the oxidation state of copper is Cu2+. Knowing the charge of the complex ion, and charge on each ligand, one can determine the oxidation number for the metal. Similarly, for this example, so tetra aqua chromium, tetra aqua dichlorochromium 3 complex. So again, aqua, water, it is a neutral ligand, no charge. So 4 into 0, then it will become 0. Then the charge for chloride ion, it is -1, 2 into -1. So the charge of chromium +3 minus 2, then the overall oxidation state of the complex, oxidation number of the complex will be +1. And then next one, coordination number. So coordination number represent the geometry of the complex. If the coordination number 2, it means linear, and then the coordination number 3, it means trigonal. Coordination number 4, it exhibits two kind of geometry. One is tetrahedral and another one is square planar. So the most commonly encountered by the complex are coordination number 4 and 6. And one important thing, so what kind of metal will form a coordination complex? So most of the transition metals only form the coordination complex. Okay, for example, as we saw before itself, chromium complex, cobalt complex, and then iron complex. So this all belongs to the transition element. So some metals such as chromium, cobalt having the same coordination number, that is coordination number 6. So coordination number 6 form octahedral. So there are two common geometries for the metal if the coordination number is 4. One is tetrahedral and one is square planar. Why square planar? And we will get so that. So it is the arrangement, that is the geometry and the arrangement of ligons with the central metal atom. So look at the example. The coordination number 2, linear, and then geometry looks like linear. And example is so phenyl chloride aqua complex, and then coordination number 3, so trigonal planar. So the example is triphenyl platinum complex, and coordination number 4, square planar. So square planar example is rhodium complex, and then coordination number 4 for tetrahedral. So the example is tetracarbonyl nickel complex. Coordination number 5, trigonal bipyramidal. So the example pentacarbonyl iron complex, and then coordination number 5, there is one more geometry, square planar pyramidal. So the example is vanadium oxide tetrachloride vanadium oxide complex, and then octahedral hexacarbonyl molybdenum complex. And then there is one more geometry for coordination number 6, that is trigonal prismatic. So the example is hexamethyl vanadium complex. And then let's see about the classification of Ligon. So the Ligons are classified based on 3 things. The first thing is based on the charge. So based on the charge, there are 3 types. One is positive Ligon, negative Ligon, and neutral Ligon. And then second thing, on the basis of the number of donor site. It means the how many number of atoms donated to the central metal atom from a Ligon. So if one atom is donated, then we call it as monodentate. If 2 atoms from a Ligon are donated, then we call it as bidentate. If 3 atoms are donated, 3 or more, then we call it as polydentate. So these are based on the number of donor atoms in a Ligon. And the last one on the basis of bonding. So there are 2 things. One is chelated ligand and another one is ampidentated ligand. So chelation means ring-like structure. So chelating ligand, it is formed either from a bidentate ligand or a polydentate ligand, which forms more than one coordination bond with a central metal atom, we call it as chelating or chelating ligands. For example, ethylene diamine and then EDTA. So this was the example. And then next one is ampidentate ligand. So ampidentate ligand, it may be monodentate ligand or bidentate ligand. So mostly it is monodentate ligand. A monodentate ligand containing two donor atoms. Let's see the example, nitro and nitrito. It containing both nitrogen as well as a oxygen as donor atom. And then let's see the example, cyanide and isothiocyanide. So this was the example where nitrogen can donate or sulfur can donate its atom, its lone pair of electron to the central metal atom. So this was the example for ampidentate ligand. So negative ligand example, most of the halogens F minus, Cl minus, Br minus and nitro, nitrito, hydroxy. So this are example for negative ligands. And then positive ligands NO2 plus and then NO plus. This was the example, and neutral ligand water and amine. Amine, carbonate. These are the frequently used neutral ligand. And then monodentate example, water, ammonia, bidentate oxalate, ethylene diamine, polydentate example, the well-known hexadentate ligand EDTA. So let's see about polydentate ligand. So polydentate ligand, as I told you, the example is ethylene diamine tetraacetate. So the formula, look at the example. Tris ethylene diamine cobalt complex. So it is the example for polydentate ligand. Therefore, ethylene diamine, it is an example for bidentate. And look at the example here, cobalt EDTA complex. So this EDTA complex, EDTA ligand has 6 donating atom within a ligand. So from this 6 donating atom, 2 are nitrogen and 4 atoms are oxygen. So this all the 6 ligand, 6 donating atom from a ligand EDTA, it will form a octahedral structure. Look at the example, cobalt EDTA, where the nitrogen are represented in blue color and the oxygen atom of a nitrogen has 2 oxygen atom. So it is represented in red color. So these are the examples, as I told you already, polydentate, monodentate and bidentate example. So chelating agents are generally more stable complex than monodentate ligands. So what is mean by chelating agents? So chelating agents, which is used to bind metal ions, so to remove the metal ions from the solution. For example, removal of harder cations from the water. So phosphate are used as a chelating agent to tie up Ca2 plus and magnesium 2 plus in hot water to prevent them from interfering with detergents. So that is one example. And then the common one is porphyrin ring. Porphyrin ring is present in hemoglobin, myoglobin. So it is one of the bioinorganic chelating agent. Porphyrin or complex containing a form of porphyrin molecule shown. So it is present in as well as hemoglobin and chlorophyll. So porphyrin or tetradentate ligand, so it contains 4 donating atoms, 4 donating nitrogen atoms to the central metal atom. If hemoglobin means iron will be the central metal atom, and then chlorophyll means magnesium. And then nomenclature of coordination complex. So from this you must know how to write the name of the complex and then how to write the complex formula. Two things you have to keep in your mind. While writing the formula, you must write the central metal atom first. Formula means central metal atom first within the coordination sphere, followed by the ligand, followed by the secondary valency ligands, and then the primary valency ligands, oxidation number. Okay, and then while writing the formula for a coordination complex, you must write the Ligon first and then write the central metal atom. So consider the complex. Yes, consider here the complex pentamine chloro cobalt 2 chloride complex. Pentamine chloro cobalt 3 chloride complex. So here this is the name, how to write the complex name. While writing the formula, look at the first one, you have to write the cobalt CO and then a neutral ligand NH3 5 times and then a charged ligand Cl and outer side the counter ion Cl2, chloride ion, anion Cl2. So from this, within the coordination sphere it is a cationic and outer the coordination sphere it is anion. So this is how you have to write the name of the complex. If the charge of the ligand is negative, we end the ligand name with O. For example, chloro, fluoro, and then cyano, hydroxocarbonato. And then if the ligand is present outside the coordination sphere, we name as such chloride, bromide, fluoride, cyanide, hydroxide, carbonate. And then oxalate ligand means we have to name within the complex oxalato, oxo, amine, carbonyl, ethylene diamine. And one important thing, if the ligand has already the name containing di or tri, considered ethylene diamine. So there are three ligands ethylene diamine, then you have to mention not triethylene diamine. You have to mention like tris ethylene diamine cobalt 2 complex, cobalt 3 complex. Like that you have to name the complex. So this was the example. Yes, and then one more thing, if the complex is an anionic complex, it is ending in changed to 8. For example, sodium tetrachlorooxomolybdate. So sodium, then we have to write outside the coordination sphere and then in the starting itself Na, and then you have to open the coordination sphere MOOCl4. Okay. And then isomerism. So isomerism, it is the secondary evolution after Turbonus theory. There are two kinds of isomerism. One is structural isomerism. So structural isomerism, it related to the same molecular formula but different bonding arrangements, we call it as structural isomerism. And another type, so for you, we are going to deal with the stereoisomerism in next class. So stereoisomerism, it talks about the same molecular formula but the ligands are arranged in the space, or we can say it as spatial arrangement of atoms around the central metal atom. There are two types of stereoisomerism. One is geometrical isomerism and another one is optical isomerism. So stereoisomerism, example for cis and trans, diamine dichloroplatinum 2 complex, and then for optical isomerism tris ethylene diamine cobalt complex, it will form enantiomas. It means it will give mirror images and which are non-superimposable. What does mean by non-superimposable? For example, the right hand gloves aren't suitable for left hand, right? So that is called non-superimposable, but it will give the mirror images. That is called enantiomas. So While next class, we are continuing with stereoisomers. So from this class, hope you all understand the introduction about coordination compound and what is meant by coordination complex. Thank you.